Hey everyone. In today's lecture, we're going to be talking about equations for chemical reactions. And so a chemical reaction is usually obvious. You can see some physical thing going on that gives you evidence that a reaction's happening. In this case, we're looking at some charcoal briquettes that are burning, and it's very obvious that there's a reaction happening, right? It's giving off fire, it's giving off heat. The black charcoal is turning into gray powdery ash. Now, how do we describe this chemical reaction on paper? Well, that's what we mean when we say equations for chemical reactions. And down below here, this is the equation for this chemical reaction. And we'll get to these symbols here in a minute. Recall from chapter 3 that a chemical change is when one substance is converted into a new substance, and that new substance has different properties. Picture here is some nails versus rusted nails. And you can see that the substance, the shiny metal, is different. Now it's like a powdery reddish orange, rust, right? The shiny metal is different than the rust. You can see that a change has occurred. It was obvious that there was a chemical reaction. Some other things that you might be able to observe for a chemical reaction are the formation of bubbles. Maybe there's a change in color. Maybe there's a production of a solid. Maybe there's heat produced. Maybe heat's absorbed. Okay? All of these are observable examples. Okay, these are things that you'll see happening that give evidence of a chemical reaction. So back to the symbols that we use. So we use a bunch of different symbols. The general scheme for a chemical reaction looks like this. We have the reactants on the left side and the products on the right side. We separate reactants. If there's more than one thing reacting together, we separate them with a plus sign. If there's more than one product, we separate them with a plus sign. The arrow indicates the separation from the reactants versus the products. The left side is what you're starting with. The arrow shows what you're forming. It's kind of like the equals sign in a math equation, but it's an arrow showing these are becoming these. If a reaction requires heat to start the reaction, like our charcoal briquette, right? The charcoal doesn't just catch on fire spontaneously. You have to light it to get it started. So the little triangle means that you had to heat it to get the reaction started. And sometimes we use symbols to specify whether the reactants or products are solids, liquids, gases, or AQ for aqueous, which means dissolved in water. So here's a table summarizing everything we just talked about. These are the symbols we use, and these are the meanings. So the plus sign separates two or more compounds. Arrow separates reactants from products. Arrow with a delta means there's heat. Parenthesis S for solid, parenthesis L for liquid, parenthesis G for gas, and parenthesis AQ for aqueous, which means dissolved in water. So going back to this chemical reaction of the charcoal, we look at our equation. We have C, parenthesis S. C, because charcoal is made of just carbon. S, because it's a solid. And it's reacting with, so we separate plus sign, oxygen gas. And the reason it's O2, remember oxygen is one of those diatomic molecules. So it always exists as a pair. Two oxygen atoms per molecule is O2. Okay, and G for gas. And so these react together to form, so we use the arrow, triangle because we had to set it on fire to get it started. And the product is CO2, carbon dioxide gas. So solid carbon reacts with oxygen gas to produce carbon dioxide gas. That's our equation. Let's look at another example. Sodium metal reacts with chlorine gas to produce sodium chloride. If you did this reaction, you would be able to observe the physical change, right? Sodium's a shiny metal, chlorine's a yellow gas, sodium chloride is a white solid powder. Right? Completely different substance with completely different properties. The equation would be 2 sodium atoms in the solid state plus 1 Cl2 gas molecule produces 2 sodium chloride solid molecules. Now, you might be asking why we have these coefficients out front. That's what we call a balanced equation. Balancing an equation means that you need to have the same number of reactant atoms as you do product atoms. It's like playing with Legos. Say you have a Lego car and you take it all apart and you build it into a Lego boat. You used all the same pieces, you just rearranged them. And so in chemistry, it's the same concept. We're not creating matter out of nothing. This isn't magic. All we're doing is rearranging the atoms. Okay? And so you got to make sure that you have the same number that you started with is the same number that you finished with. Right? You have to account for all the atoms. So in this equation here, we had 1 carbon atom and 2 oxygen atoms on the left side. And then on the right side, we still have 1 carbon and 2 oxygens. So let's practice writing a balanced chemical equation from a sentence. Aluminum metal reacts with sulfur powder to produce solid aluminum sulfide. Write a balanced chemical equation for this reaction. Well, we're literally going to take the words of that sentence and convert them into symbols. So aluminum, what's the symbol for aluminum? Al. And metal. Metals, are they usually solids, liquids, or gases? Usually metal is a solid, especially if they specify that. So aluminum metal, so Al, parentheses S, reacts with is going to be plus sulfur. Sulfur is just S, and powder. Is that a solid, liquid, or gas? It's going to be a solid. So parentheses S, to produce, arrow, solid aluminum sulfide. Now, aluminum sulfide is going to be Al2S3 and solid, parentheses S. Now, how did we know that it was Al2S3? Recall from chapter 6. Whenever you have an ionic compound made with a metal and a non-metal, they're going to be charged ions. And we know that aluminum always forms a 3+ charge. And we know that sulfur always forms a 2- charge. And so to balance those charges, you need 2 aluminums and 3 sulfurs. 2 times 3 is 6. 3 times 2 is 6. So that's our balanced ionic compound. And so there's our chemical equation from that sentence. But it's not balanced yet, right? The next thing we have to do is we have to balance it. So to balance the chemical equation, what we usually do here is we draw a line between the reactant side and the product side. And the number of atoms on the reactant side has to be equal to the number of atoms on the product side. So on the left side, we only have 1 aluminum and 1 sulfur. On the right side, we have 2 aluminums and 3 sulfurs. So what we do is we add coefficients in front of the compounds to make it balance. And so putting the 2 and the 3 as coefficients gives us 2 aluminums and 3 sulfurs, so that we're equal to the 2 aluminums and 3 sulfurs. So you got to make sure that each element matches up, has the same number on both sides, and if they do, you are balanced and the reaction's done. So that's a balanced chemical reaction right there. Let's do another practice problem. State the number of atoms of each element on the reactant side and the product side. So we're going to split down the middle, and we're going to look at each element in the reaction. So we have carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen. And we need to tally them up. So carbon on the left side, I only have 1 here. And on the right side, I only have 1 carbon as well. So that's good. Hydrogens. On the left side, I have 4 hydrogens here. Now on the right side, I have H2O, but there's 2 of them. And so I'm going to multiply 2 times 2, give me my 4. And then oxygen on the left side, I have 2 O2s, so those multiply to give me 4 oxygens. And on the right side, I have 2 in the first compound and 2 in the second compound, so that's a total of 4 as well. So everything is balanced. Now, a lot of students get confused, and so I made this slide to try and clarify for you. A coefficient, shown in blue, is the big number out front. That tells you how many of an entire compound you have. So when you see 2 H2Os, that means I have 2 separate molecules of H2O. The red subscript number tells you how many of that atom there is within the molecule. So the H2O tells me that there's 2 hydrogens in a water. The blue 2 tells me that there's 2 entire waters. And so when we're trying to look up the number of hydrogens here, you multiply the coefficient times the subscript, and that gives you the number of atoms total. So here the 2 times O2 gives me 4. So multiply the subscript and coefficient to get the total. Let's do a study check. State the number of atoms of each element on the reactant and product side for the following equations. Okay. So split it down the middle. For the top equation, we have 2 elements. We have phosphorus and we have bromine. Now, how many phosphorus atoms do we have? I see 4. And then for bromine, we have 6 Br2s, so we're going to multiply the 6 by the 2, and that's going to give us 12 bromine atoms. On the right side, we have 4, and there's only 1 phosphorus in this compound, so that's 4 phosphorus atoms. And then we're going to multiply the 4 by the 3, and that's going to give us 12 bromine atoms. And it looks like everything's balanced. Now on the bottom, let's take a look. We have aluminum, iron, and oxygen. So let's tally them up. I see 2 aluminums on the left, and on the right side, I see 2 aluminums. Now for iron, on the left side, I see 2 irons. On the right side, 2 irons. And oxygen, I have 3 on this side and 3 on that side, so everything's balanced. Let's do another study check. Balance the chemical equation when solid Fe3O4 reacts with hydrogen gas to produce solid iron and liquid water. So the first thing we got to do is convert that sentence into an equation. So solid Fe3O4 is going to be Fe3O4. Solid is parenthesis S, reacts with plus hydrogen gas. That's H2 because hydrogen is one of those diatomic molecules. To produce, arrow, solid iron. That's going to be FeS and plus liquid water. So water is H2O and liquid is parenthesis L. Okay. Now, we need to balance it to make sure we have the same number of atoms on every side. Okay. So if we're looking at the iron here, I see that I have 3 of them. But on the right side, there's only 1. So that means I need to put a coefficient of 3 to give me the 3 irons. And then for oxygen, I have a subscript 4, which tells me that there's 4 oxygen atoms here. But on this side, there's only 1. So I have to put a coefficient 4 to give me my 4 oxygens. And then for hydrogen, on the right side here, I have 4 times 2, so that gives me 8. And then on the left side, I have 2, so I need to put 4 there. That way 4 times 2 gives me 8. And then we're balanced. And so we had to add the coefficients here, make sure we had the same number of atoms on the left side as we did the right side. Now, to make it a little more complicated, we're going to do balancing some reactions that have polyatomic ions. It's not any harder. It's the same concept, but it just looks a little more confusing. Let's do an example. We're going to balance this equation here. Now, I want you to notice the nitrate. We have NO3 on the left side, and then on the right side, we still have NO3. NO3 is a polyatomic ion, it's nitrate. If your polyatomic ion doesn't break apart, just treat it like one whole thing. So when we're balancing, I'm just going to look at NO3 as a unit. I'm just going to treat it as one thing. Okay. And similarly, we have a carbonate, CO3, on the left and a carbonate on the right. The carbonate didn't break apart, so I'm going to treat it as one thing. Okay. And we also have iron and sodium. Now, when we're balancing equations, the trick that I like to use is look for the most complicated compound and start with that. So in this case, I think that the iron carbonate looks like the most complex. It's got the largest coefficient, or excuse me, largest subscripts. So I'm going to start with this compound here. And we see that there's 2 irons. So I have 2 iron atoms. And for carbonate, I have 3 of them. So when we go to the left side here, I only see 1 iron atom, but I need 2. So I'm going to add that coefficient 2 right there. That gives me 2 irons. Now, for carbonate, on the right side, we had 3 CO3s. On the left side here, there's only 1. So I need to stick a coefficient of 3 to make sure I get the 3 carbonates. Now let's look at nitrate. I have 3 nitrates in the compound, but I have 2 of that compound. So 2 times 3 is 6 nitrates. And sodium, I have 3 times 2. So I have 6 sodiums. So what I'm going to do is go back to the right side, and I'm going to stick a coefficient of 6 up there. That gives me my 6 sodiums, and that gives me my 6 nitrates. And it looks like everything is now balanced. So we are done. So 2, 3, 6, 1. And it looks like we did it right. Okay, let's do a study check. Let's fill in the coefficients to balance the following reactions. So we're going to plug in numbers here to make sure we have the same number of atoms on the left side and right side. Well, the first thing I notice here, looking at the most complicated thing, is that we have O3. So that's 3 oxygens. On the right side, I have 2 oxygens. So what am I going to do? I'm going to flip-flop those numbers. I'm going to put a 2 here and a 3 there. And that's going to give me 6 oxygens, right? 2 times 3 is 6. 3 times 2 is 6. So oxygen's balanced. But that's going to give me 4 irons. So I'll stick a 4 there to balance iron. And then the 3 carbon dioxides means I need 3 carbons. So that should be balanced. Let's look at the next one. The most complex thing here is the aluminum oxide. And we can see that it has 2 aluminums and 3 oxygens. So if I have 2 aluminums, that means I need to put a 2 here. And if I have 3 oxygens, I have to put a 3 here. But then that's going to give me 3 irons. So I'll come back and put a 3 there. And that should be balanced. And then for the last one, once again, let's start with the most complicated compound. This looks pretty complicated to me here, this aluminum sulfate. And we see that there's 3 sulfates. So I'm going to put a 3 here to balance the sulfate. And the 2 aluminums, I'm going to put a 2 there. Now, when I put the 3 here in front of the H2SO4, that gives me 6 hydrogens. So I'm going to come back and put a 3 here to give me 6 hydrogens. And we should be balanced. All right. Thanks for watching, and that's the end of this video. I'll see you in the next one.